When we talked about the magnetic force, we introduced the idea that magnetic fields are caused by currents. And so for this class, there are two types of current carrying wires that we're going to focus on when thinking about the magnetic field caused by those two wires. The first of these will be a long straight wire. And basically we're going to think about this as an infinitely long straight wire. We're going to be interested in the magnetic field at point P caused by this long straight wire. Our other option will be when we have a current loop. And in this case, we'll be interested at the point P at the center of the loop. We'll have a conducting wire carrying some current around in a circle, and we'll talk about how to calculate the magnitude and direction of the magnetic field at the center of that circle. So let's start with our long straight wire. So I want to think about the magnetic field at a point P that's located a distance r away from a long straight current carrying wire. I can calculate its magnitude as equal to mu naught over 2 pi times I over r. And so I, of course, is the current in the wire, and r is the perpendicular distance from the wire to point P. So let's pick a point P out here, and I'll label this P1 because we'll look at multiple points around this wire. The equation on the screen gives me the magnitude of the field, but what I need to recognize is that the field will be perpendicular to the plane in which the current flows and that connects your current to point P. So another way to think about this is that we can start by drawing in R. So there's the line that connects our wire to the point P along its shortest possible distance, right? So this is the perpendicular distance from the wire to point P. The magnetic field generated by that current at point P1 has to be perpendicular to both the current and the line that connects the wire to point P. Which means if my current is flowing out towards me, right? Again, this symbol tells me that the current's flowing out towards me. So my current flows out, R points to the right. That means that the magnetic field will be perpendicular to the horizontal plane running in and out of the screen. My field vector has to point either up or down. And again, there'll be a right-hand rule. If you take the thumb of your right hand, point it out with the current, turn your right hand so that your fingers point to P1, then again what you notice is your palm is pushing up. And so sure enough, that tells us in this case that the magnetic field at point P1 points up. Let's pick a different point. So let's look at P2 that's sitting up above the wire. Well, again, the current still points out. I can draw in the line from the current to the point. I know that the magnetic field has to be perpendicular to the plane defined by the current and the line running to the point, which means in this case that the magnetic field has to lie along a horizontal line because the current and the line to the point define a vertical plane running in and out of the screen. I'm going to take my right hand, put my thumb in the direction of the current, point my fingers towards P2. What I notice now is that my palm is pushing to the left, and so I get a magnetic field vector that points to the left. Again, we can keep circling around, and so if we do the same thing at point 3, again, I'll have a magnetic field that is perpendicular to the line that runs from the current to point P. My right hand rule tells me in this case the magnetic field at point 3 points down. If I pick a fourth point that's now below the wire, the magnetic field vector points to the right. And so what I can see is that as I keep adding more and more points, I notice that the magnetic field is circling around my long straight wire. The easiest way to think about which way the magnetic field circles is, again, take your right hand, point your thumb, the thumb of your right hand, out of the screen towards you, and notice that the fingers of your right hand curl counterclockwise the same way that the magnetic field is circling around the wire. The other wire that we're going to look at is the magnetic field generated at the center of a current carrying loop. So here I have a current that is moving around some wire in a counterclockwise direction. I can get the magnitude of the magnetic field at the center by mu naught over 2. So notice there's no pi here. Mu naught over 2 times I over r. So big R is the radius of the circular loop. In this case, the magnetic field points out towards me. And again, that's coming from a right-hand rule, because if you take your right hand and curl your fingers counterclockwise, like the current loop, notice that your thumb is pointing out towards you. So that's the right-hand rule that gives us the direction of the magnetic field for a current-carrying loop. And so here what we can conclude is that the magnetic field runs straight through the center of a circular loop. So we flipped what's straight and what's circling. For the long straight wire, what's straight was the current, what's circling was the field. For our current carrying loop, what's straight is the field, what's circling is the current. Now we'll often think about current carrying loops and the fields that they generate, so we'll only be able to calculate the magnetic field at the center in terms of using mu naught I over 2r. But if we draw in all the field lines for the magnetic field generated by that current carrying loop, what you notice is it looks just like the field generated by a bar magnet. So current loops act like bar magnets. So let's summarize. Again, we're going to focus on two types of current carrying wires for this class: an infinitely long straight wire and a current carrying loop. In both of them, something is straight and something circles. For the long straight wire, it's the current that's flowing straight along the wire and the magnetic field circles around the wire. For the current loop, it's the current that's now circling, and so we can think of the magnetic field coming up through the center of that loop is what's now straight. Two very similar but different equations. And so the reason I'm writing one as a lowercase r and one as a big R is to help draw the distinction that one is simply a distance to the point P in space, the other is the radius of the loop. To get directions for both of these, we're going to use our right-hand rules. And so we'll get plenty of practice in class making sure that we get the correct directions for the magnetic fields for both our long straight wire and our current carrying loop using our right-hand rule.